This one. This is probably better.
Let's wait for it.
Yeah.
There is a way in Italian to say pochi ma buoni.
Pochi ma buoni.
Pochi ma buoni.
Ma buoni.
Few but very good ones.
Yes, that's what I need.
Okay. And let's wait still a moment because when you is missing, and I would like him to be here. And needless to say, your talk have been very, very important. And now we have to work very hard to coordinate various activities in preparation of the course.
Mm-hmm.
And I see the key point we have to involve all the space mission and ground observation in relativistic astrophysics from China. All the groups. Therefore, this has to be a very methodic approach. Tomorrow we are going to have a very nice presentation. You are still there to here tomorrow morning?
I'll be here in the morning. My leave at 2. 2, yeah. 1:50. I need to leave at 1:50. Bus.
Per favore, system manager. Grazie molte. Saremo usciti. Lo riattivi, sì. Grazie. We have an alarm system.
Yes,
at
yeah.
9 o'clock. Therefore, I had to call them to give us 2 hours time without alarm.
Mm-hmm.
And this has been achieved. But I don't see, because we lost now Raim. Where is Raim? I saw him in a moment and disappeared. Hello? Where is Wagyu and Raim? They are coming?
I don't know.
You're preparing for the day after tomorrow. Okay. I don't understand why. Did you see Wagyu or Raim? Anyway, I can happened to them. And Raim was here a moment ago, and I noticed he went away, and Wu is not here either. But there is no reason we cannot go on. We have the great pleasure to have one of the people who participate with us on the founding of GRB. And he has written beautiful books, and he has guided a pioneering group in US, and now, like many of the scientists, because you disappear. I want to bring him. And he founded a very important group in Northern America, in Salt Lake. No, was not Salt Lake. Where were you? In that beautiful part on the Pacific. You were
Nevada,
Nevada.
Las Vegas.
Yes. And now he's in Hong Kong. And we all look forward to a strong development there. And he already managed to make a journal in relativistic astrophysics with Elsevier, in which we had the honor to publish. And now, interesting enough, although from US he moved to China, he has been asked to be one of the key editors of APJ recently. This is a great occasion for APJ to reestablish some credibility, and I am very, very happy of this initiative, which enters in a new revival of relativistic astrophysics, which has seen, even today, not only the presentation of Wing Zhang, but the most remarkable presentation I think you all heard about Di Li from the largest telescope in China, FAST, this morning. No, Di Li. Yes, not you, Di Li. Okay. Anyway, we are very happy to have him here, and please, this evening he will address multi-messenger astrophysics in GRB. I look forward to his presentation. If you like the microphone, okay. Or
This one works. Yeah. Thank you very much, Remo, for the invitation and for the nice introduction. So continue on the introduction of fast radio bursts in the morning. So I move on to discuss broadly multi-messenger astrophysics. So let's start from this slide. For thousands of years, human has been using naked eye to observe the universe. And since the invention of a telescope by Galileo, we start to extend our eye to more deeper, higher resolution, and more importantly, expand to the entire electromagnetic spectrum from radio all the way to gamma rays. And on this slide, so I show some of the state-of-the-art telescopes. So this is the China's FAST, Keck, Hubble Space Telescope, Chandra, and Fermi. So we have been seeing the cosmos for thousands of years, hundreds of years in the modern era. But nature has four fundamental interactions, and each actually carries a new messenger. So besides the photons, which is the messenger of electromagnetic interaction, we have neutrinos from weak interaction, cosmic rays from strong interaction, and gravitational waves from gravity. So not only we are seeing the universe, we are smelling, we are touching, and we are listening to the universe. And this multi-messenger view of the universe is actually more relevant because the universe is not the steady state. It is evolving, and we see all the stars, and stars eventually, at the end of life, will produce white dwarfs, neutron stars, and black holes. And in particular, once we have these compact objects, we can have very short duration activities in the universe. So this is the transient astrophysics field. So from radio pulsars, FRBs, X-ray bursts, creating black holes, supernova, gamma ray bursts. And this is merger of black holes, merger of neutron stars and black holes, and long duration gamma ray bursts, short duration gamma ray bursts, AGN jets. So the universe is a violent universe. And one of the most exciting field in astrophysics is this high energy transient astrophysics. So I generally classify all these objects into three classes. So type 1 are those related to the compact, stellar-sized compact objects, including black holes, stellar black holes, neutron stars, and white dwarfs. And type 2 are those regular stars, but at the end of their life, they start to form these things. And a lot of activities are, a lot of transients are related to the death of the stars. And the third type is supermassive black holes or intermediate mass black holes in the center of the galaxy. So all the high energy transients probably can be classified these three types. And there are also non-catastrophic ones, which means after this event, the engine doesn't die, it's still there. So it will produce repeating events. In the radio band, we have radio pulsars, repeating FRBs. In the stars, we have stellar radio flares, radio jets from AGNs, lobes. And in optical band, we have novae, optical flares, AGN variability. So these are all repeating. X-rays, X-ray binaries, bursts, X-ray flares, AGN outer bursts. And in gamma rays, so there is one type of objects called soft gamma ray repeaters. So they're magnetars. They produce gamma ray bursts, but on and on. And then we have a binary system where gamma ray flares, blazars have this gamma ray variability. So these are the non-catastrophic ones. And more spectacular are the catastrophic ones. So this is just one-off events. So in the gamma ray band, we have short GRBs or type 1 GRBs, long GRB, type 2 GRBs, and TDEs, jetted tidal dispersion events. And X-rays, we have fast X-ray transients, which I'm going to talk about a lot today. Both type 1 and type 2, and there's X-ray TDEs. Optical, we have type 1A supernovae. It is related to compact objects like white dwarfs. But we also have type 2 1B, 1C supernovae, which is related to death of the massive stars. And then we have optical TDEs. And in the radio, we have probably some non-repeating FRBs, radio afterglows, and radio TDEs. So working in this multi-wavelength, multi-messenger transient astrophysics, how does it like? It's just like these people running. So it's highly competitive and intense and pressure, because I have been working in this field for more than 2 decades. It's just when nobody can predict anything will happen, but when it happens, all the astronomers in their globe will start to run, and within 1 week, something needs to be produced. Theorists want to write quick papers to explain things, and the observers will through all the telescopes to observe them. So it is very tiring, competitive, intense, and pressure. On the other hand, it's also a lot of fun. So that's why a lot of people are working on this, because we essentially we are like Sherlock Holmes, because we don't know what is happening. We look at these fingerprints, footprints, and smoking guns, and trying to figure out what is going on. And we are entering this new era of multi-wavelengths and multi-messenger astrophysics. I list some of the most used and best telescopes right now. So in the gravitational side and the neutrino side, like on the IceCube, these are still in the US. The other four, which I'm heavily involved in, Einstein probe, SWAN, FAST, and LASSO, they're all in China. So that is part of the reason I relocated from the US to China, because I'm using all these telescopes all the time. So I will go through some of these discoveries with these telescopes a little bit later. So multi-messenger, we have 4 types of messengers. Let's go through one by one how to produce photons. So this is probably the easiest one. And in the morning, I talked about the black body thermal, incoherent non-thermal, coherent non-thermal radiation. But this is another way of talking about photons. So in a classical picture, so as long as we have a charged particle, as long as it is accelerating, photons will be released. In a quantum view, so we have atomic levels and jumping between different levels where photons are released. And at QED, so photons are just boson mediator of electromagnetic interaction. So these are 3 levels of understanding photon radiation. And here I'm talking about, so all the astrophysical objects, they emit light of different forms, but underlying fundamental power are these 4 types: gravitational energy, for example, through accretion, through TDE. So these things are powered through gravitational energy. So we have rotational energy, for example, black hole, blend first Nyack, or pulsar spin down. So we are making use the rotation kinetic energy of the objects. Nuclear energy, we have the sun, we have type 1a supernova, we have kilonovae, so those are related to nuclear reaction and releasing photons. And finally, we have magnetic energy, so typical examples like solar flares and magnetars. So these are different ways of producing photons. And how to produce gravitational waves. Then this is the Einstein equation. We all know that energy, momentum, and matter tells how the space-time is curved, and the curvature tells how matter moves. And then if we do some small perturbation and we remove the source term, and it turns out that it is a wave function, and these are gravitational waves, but these are the wave of the space-time oscillation instead of the matter in the space-time. And most importantly, it is quadrupole radiation, which means for electromagnetic radiation, we need acceleration of the charge, but here we need to have the change of the acceleration. We need to have the third derivative, so we need to have the acceleration of the acceleration. But it's not that difficult to produce this, simply because for binary systems, that's the acceleration, the force direction is changing. So naturally, all the binary systems are gravitational wave emitters. And then the luminosity can be cast into this simple form. So for equal masses, in very simple form, then we have this fundamental constant defined maximum luminosity, which is 10 to the 59 ergs per second. So it is defined by c to the 5th power divided by g, and they are all fundamental constants. And then It is related to this Rs over a to the fifth power. Rs is the Schwarzschild radius, and a is the separation between the two. So you can see, because it's the fifth power, so when this number is small, then the gravitational wave is very, very weak. And when the two objects are very, very close to each other, for two black holes, this is very close to each other, then this term becomes very large. So that is why the top candidates for gravitational wave radiations are these compact object mergers, black hole mergers, neutron star mergers, neutron star black hole mergers, or CBCs, compact binary coalescence. So in order to produce gravitational waves, we need to have massive objects, we need to have compact objects, and change of acceleration. And how to produce neutrinos. Neutrinos are related to weak interaction, and this is the standard model for particle physics. We have quarks, we have leptons, and leptons we have we have charged leptons and also have neutrinos. And usually, in order to produce neutrinos, we need to turn into proton to neutron or vice versa. So in the nuclear reactions, whenever you turn a proton to a neutron or vice versa, you actually you need to produce a extra charged lepton, and in order to conserve the leptonic number, and neutrinos are produced. So nuclear reactions are the sites to produce neutrinos. And another possibility is just through so-called photon-meson interaction. The protons directly collide with light and produce pions, and pions start to decay. So in this case, we can start with a proton and eventually make neutrinos. So the bottom line, to produce, to be a significant neutrino emitter, we need to either have a significant nuclear reaction, or we need to have accelerated protons or ions, and also a very dense photon target field or matter target field. So this is how our neutrinos are produced. And finally, cosmic rays. So cosmic rays are nothing but just ions. But what matters is you need to leave the source and get throughout to the space. So we need to have some acceleration mechanisms. And the acceleration, the maximum reachable energy depends on the size of the source and the strength of magnetic fields. This is the famous Achilles plot. And the way to accelerate these particles, we can have the standard Fermi acceleration through turbulence, second order, and the first order through shocks. And also another possible acceleration site is the reconnection. And the reconnection is rich in form of acceleration mechanisms. You can do Fermi type of acceleration. You have parallel E field that can also accelerate. So these are the different sites of astrophysical accelerator. So we need to charge the baryon acceleration. So we need the size and magnetic fields, and also Lorentz factor to boost it up. So this is how to produce cosmic rays. And so multi-messenger astrophysics, multi-messenger emitters is something that can produce photons, can produce neutrinos, can produce gravitational waves, and also these cosmic rays, and eventually reach the Earth. And cosmic rays, usually because of their charge, you cannot trace back to see where it comes from. But all these three other messengers, we can pin down the direction, and we can figure out where it comes from. So this is a current summary of the multi-messenger emitters. So here is gravitational wave emitters, here are the electromagnetic emitters, neutrino emitters. And it turns out that so far we already found that at least several objects emit two messengers. For example, neutron star mergers, they produce gravitational waves, they produce GRBs and kilonovae. And AGNs and supernovae, they produce neutrinos and EM waves, of course. What is the most likely object that can emit all three? The GRBs is probably sit right in the middle. However, so far there's no neutrino directly detected associated with any GRB. So actually, the ice cube was built with the purpose of detecting neutrinos from GRBs, but so far it was not detected. So I'll explain why a little bit later. But some others, so far they can only produce EM, but there are some report, for example, TDE might be associated with neutrinos, FRBs might be associated with gravitational waves, but these are not confirmed. So that all the dashed lines are not confirmed, theoretically motivated ones, but the solid lines are the solid, robust detections. And in the rest of the talk, I'll focus on these three subjects: gamma ray burst, fast X-ray transients. These are new transients discovered by Einstein probe, and a little bit faster radio bursts again. So the story one is gamma ray bursts. This is the most energetic, most luminous explosions in the universe. And we start with this physical picture. So I start to put on my theorist hat. So I have been working on the gamma ray burst physics for 2 decades now. So the general picture is you probably have some progenitor, massive star collapse, new mergers, and produce a central engine black hole or magnetar. And then this relativistic jet released, and then we have photosphere, internal shock, external shock, and so on. So this is the physical picture, but there are a lot of open questions. And Remo mentioned about this book, and it was my honor to give a signed copy to Remo for comments. And a lot of these subjects have been discussed. Open questions are discussed in the book. Progenitors and classification, whether it is massive star core collapse or compact star mergers, or whether it is binary, as Remo's group has been discussed a lot, or just a single massive star. Central engine, whether it is a black hole or millisecond magnetar. So this morning we heard 2 talks. One talk about the black hole and the other neutron star. So the central engine, we don't know. And ejecta composition, so whether it is a fireball, matter dominated, or maybe magnetic Poynting flux dominated outflow. So this is also subject to debate. Energy dissipation mechanism, whether it is through shocks, which if it is matter dominated, then mostly dissipate energy in shocks. Otherwise, it is through magnetic reconnection. Particle acceleration and radiation mechanisms, synchrotron, inverse Compton, quasi-thermal, and afterglow physics, medium interaction, or maybe afterglow itself is just produced by the central engine. So it's a lot to discuss, but I will discuss 6 highlights in the recent years. The first one is this gravitational wave association. I think this has been discussed a lot. But the bottom line is neutron star mergers are now prove that they can produce short gamma ray burst and kilonova. So the very nice kilonova light curve is consistent with the model prediction, even though it's a little bit brighter. And then there's a 1.7 second delay between the gravitational wave and the short gamma ray burst. There's many discussion why it is that, and my favorite personal scenario is that it takes a while for the jet to reach the dissipation radius, and that the duration of the emission and the duration of the lag is of the same order. So it's consistent with the jet is promptly launched, but it takes a while, one point some seconds, to reach the dissipation region. Okay, so that was very interesting. So short GRBs are known to be produced from neutron star mergers. And then the second highlight is very recently there are these outliers. Actually, back in 2006, we already discovered one case, 0606 14. So it is a long duration, but without the supernova. So back then, I published this article in Nature. It's in, News and Views. But in any case, I said, okay, don't call these long and short anymore. Let's just call them type 1 and type 2. Type 1 are related to mergers, and type 2 relate to massive star core collapse. But there was resistance in the community because observers like to use long and short, and that's fine. But until very, very recently, all these oddballs jump out. So this one is a short duration, very short duration, but it was associated with the supernova. So it is definitely a type 2 massive star core collapse event. And these two are very long, long duration bursts, but they are associated with kilonova. So these are related to compound star mergers. So again, so we need to go back to this physically defined classes. And the highlight number 3, this also happened in very recently in 2022. So this was the bold GRB, brightest of all time. So it is so bright, it was so bright that it deviates from this fluence distribution. So this is when you see a burst when it is brighter, then it should be much rarer. So for this type of it's so bright, so usually it should happen once every 1,000 years or 10,000 years. And we were so lucky that within our lifetime, one thing just happened. And it turns out that this GRB was at the zenith of the LASSO China, the TeV telescope. And in the TeV band, it detected more than 10,000 photons, a lot of photons in TeV. So you can imagine how energetic that burst was. And it turns out that the entire afterglow is not the standard synchrotron radiation. It is the inverse Compton scattering. So, and also it has a very, very narrow jet. So usually the jet break happens in hours. The jet opening angle is 5 degrees. And this one is ½ degree. So it means that it's very, very narrow pencil beam pointing towards us. And the distance is also quite nearby. So that's why it was extremely bright. Of course, outside this very narrow jet, there's also structured jet wing outside. There's a lower energy, but there's still emission there. So this is the funny part. So imagine that because this is once every 10,000 year, 1,000 year or 10,000 year. So the last time when this thing happens, it was in Song dynasty in China, or when humans were still in the cave. So that was the last time when it happens. And the next time when it happened, either 1,000 years later, we are living in a very prosperous world, or maybe it has been conquered by machines. So 10,000 years later. So we were so lucky to detect this one, and we learned a lot from this boat GRB. So this was highlight number 3. Highlight number 4, around the same time, this was the second brightest of all time. So very interestingly, the 2 brightest GRBs happened within 2 years. And this one is 230307A. And this one was also the one that is the long duration GRB with the kilonova. So duration is pretty long. Just look at this light curve. It's pretty long, but it is not a collapsar. It is not a massive star core collapse. It is related to some neutron star mergers, maybe white dwarf neutron star mergers. But what makes this interesting is if we look at this gamma ray light curve all the way to X-ray light curve, the gamma ray all the way to 0.5 keV, everything behaves consistently. It is the single jet component. And when we go to softer band, it becomes wider. However, when we get to, say, below 0.5 keV, it behaves very differently from the higher energy emission. So it is consistent with the underlying central engine. So this burst, we clearly see the onset of the emission from an underlying central engine, which is a magnetar. It is consistent with a magnetar. So we know that the merger of the two neutron stars, if it is, or maybe a neutron star and a white dwarf, eventually launch a jet, produce gamma rays, but left behind a rapidly spinning magnetar. So that was another major advance, because I said there was debate whether it is a neutron star or a black hole. And this is the same burst. This same burst also tells us a lot of interesting things, because the light curve has two components. One is the slow component, and on top of that, there's a very rapid variability. So the slow component has a nice relation. So when you go to softer band, it becomes wider. So it means that the emitter itself is moving outwards towards a larger and larger distance. However, if you look at the rapid variability, including the spikes and dips, they align with each other at different energies. So this tells us within this big emission region, there are small mini jets everywhere inside this large emission region. So this suggests that we have jets inside jet. And it is consistent with a Poynting flux dominated flow, because only you can, when you have a magnetized emitter, you can launch mini jets. The sigma, the Lorentz factor is 1 over square root of 1 plus sigma. So this tells us that not all GRBs are fireballs. At least some of them are Poynting flux dominated outflow. And this was my proposal called the ICRANet model a while ago, back in 2011. I predict that we should see such kind of signatures, and now we see from this event. So this is another interesting fact. This has the implication of this final highlight number 6. So this is the non-detection of neutrinos, because as I said, IceCube was built initially to detect neutrinos from GRBs. But after many, many years, no neutrino, they detect a lot of neutrinos, but none of the neutrinos came from a GRB. So this is the prediction, and these are upper limit become much lower than that prediction. That prediction is the standard internal shock model. And this was from the IceCube collaboration. They published several papers. So this is probably from 2016. They said, okay, these are the regions that parameter space that are ruled out. So for standard, that's the internal shock. This is the photosphere model. So those two models are suggesting that GRB emission coming from small radius from the central engine. So those models are ruled out by IceCube. Only, so the ICRANet model was my model. So this is the typical parameter we are talking about. So it is still consistent. So all these non-detection is consistent with the emission region, which is far away from the central engine. So it is magnetized central engine. So this is, in some sense, it is similar to the solar neutrino problem, but it's different outcomes. Back many years before, we also missing some neutrinos from the sun, and we don't know whether it's astrophysics that's wrong or physics was wrong. And it turns out physics was wrong because the neutrino is oscillating. And for GRB, they also have this neutrino problem because none of the GRB have, even the brightest of all time, there's no neutrino detected. But this time, very likely it was not because of physics. Maybe physics is still something we're missing. But assuming that physics, everything is correct, astrophysics was wrong, because previously people considered standard fireball matter-dominated jets. So in reality, most of the GRBs are Poynting flux dominated, and the emission region is much, much farther away from the central engine. As I said, neutrinos, we need to have p-gamma interaction. Proton will interact with photons. And what we see is just the luminosity. We know how many photons are emitted, but what is the photon number density, we don't know. If the emission region is small and all the photons are packed in the small region, and the protons will hit those photons with a high optical depth, and they will produce a lot of neutrinos. And my model is saying that the dissipation radius is way far away from the central engine. It is close to the deceleration radius. So given the same amount of photons, the photon number density is much lower. Optical depth is much lower. So that's why there was no neutrinos detected from GRBs. And now we move to the new GRB era called SWAN. So this was launched in 2024. So it's a Chinese-French gamma ray burst mission. And I now put on my hat as the Chinese mission scientist. And so the SWAN, this was the observation is still going on, but these are the first 9.3 months. Okay, so if you go back one slide earlier, so SWAN is basically the combination of Swift and Fermi GBM. So ICRANet is a French detector, so this is something like a bat, but it's softer. So this is the soft gamma ray detector. And there's also a GRM, so this is like Fermi GBM. So this is harder gamma rays. So SWAN can detect both softer gamma ray and harder gamma rays. And then, like XRT, there's MXT, even though the MXT is less powerful than Swift XRT, but it carries a huge visual telescope, VT, and this VT is actually much more powerful than UVOT. So this is why, so we have GRM triggered only, ICRANet triggered, and also the joint trigger. So as long as we have onboard trigger, 100% of the GRBs will have X-ray afterglow detected, and optical afterglow, and the redshift, more than half can have redshift measurements. So just give some highlights. So SWAN is regularly detecting a lot of all kinds of GRB, short and long. High redshift, there is already 7.3 redshift GRB detected. X-ray rich, X-ray flashes, central engine activities in optical. A lot of results are still being written, and it takes a while to publish. But this was already published in ANA. So this was a long gamma ray burst detected by ICRANet, and it was identified to have redshift 7.3. Why is that? Because VT is very, very sensitive. It turns out that there's no detection in VT, which means it has to be high redshift because lambda alpha absorption will shift to the optical band. So the non-detection in VT is a good indicator, and people go to the infrared telescopes and found the afterglow and start to measure the spectrum and eventually measure the redshift 7.3.
This is the source we were interested in you. Okay. We have to look at.
Yeah. And interestingly, this one also had a gamma ray burst as a supernova associated. So there was a supernova detection at 7.3, and that supernova, this one, supernova is not that different from nearby supernova, which means that at 7.3, the GRBs behaved quite similarly to the GRBs nearby. And there are some other highlights because they're not published, so I will skip them today. Then I move on to the story number 2. So fast X-ray transients. So what are these? They are just X-ray bursts. So we have gamma ray bursts, we have X-ray bursts. But because X-ray bursts have been used to describe the accreting neutron stars, so people use these different words, fast X-ray transients. And these are the counterparts of gamma ray bursts, the cosmological explosions, but peaked in X-rays. So before EP, there have been already some detection of fast X-ray transients from Hattie-2, Swift, Chandra, XM, and Newton, but there was no systematic follow-up. Swift detected this low luminosity gamma ray burst 060218, but it had the gamma rays, not just the X-rays. And it was nearby and also with a supernova. And then there was a shock breakout event, 2008. So this one had the luminosity much, much lower, 10 to the 43 erg per second. So these are the indicator that in the X-ray sky, there should be a lot of transients. And people searched from archives from Chandra and XM Newton archival data. They found a lot of these transients. So EP was launched. Einstein probe was mainly the Chinese mission, but there's a collaboration from ESA and MPE. It's a wide field, high sensitivity X-ray survey telescope, and I put on my EP hat as a science management committee member, and I'm also chairing the multi-messenger science working group. So Einstein probe made a lot of breakthrough discoveries. So it also has a Chinese name called Tianguan. So it carries two detectors. One is wide field X-ray detector. So this is the triggering telescope. Because it has this new technology, lobster technology, it is much more sensitive than previous detectors, and also have a wide field view greater than 3,600 square degrees. So it detects a lot of transients in X-rays. And there's also a follow-up X-ray telescope on board. So this one is much more sensitive. Once you see something, you throw over and look at the afterglow emission. And this was the detection of these EP objects. So they just call EP, name everything under EP. So all the transients are like this, but fast X-ray transients, these are the ones that confirmed of cosmological origin, because there are a lot of, say, X-ray flares from stars as the contamination. But we already, roughly speaking, 100 fast X-ray transients per year. And because of these triggers, a lot of follow-up observations from optical, from radio, we can start to figure out what these objects are. And it turns out that there are, again, three types: type 1, type 2, type 3, neutron star mergers, massive star core collapse, supermassive black holes. So most of them are type 2, massive star core collapse. So we'll start with this one. So this was the very first EP detected event with the redshift measurement. And it turns out the very first one, redshift is 4.859. And look at the observation. So it had a gamma ray burst association. This red bar is the GRB. GRB is pretty short. It's only 10 seconds. But if look at X-rays, much, much longer. So previously, we know that after the gamma ray burst, we have a softer X-ray emission. Those are called X-ray flares. But because of EP, we start to see that even before the gamma ray burst, we already have soft X-ray emission. And this tells us that the emission, the so-called gamma ray burst we see does not mean the entire thing. The entire thing is buried. We usually cannot see it. But with X-rays, we start to see that before this bright gamma ray jet comes out, something is already going on. So this paper was published in Nature Astronomy in 2025. And this is another interesting case, also Nature Astronomy. So this one, instead of a very high redshift, this is very low redshift, 0.4. And this one does not have a gamma ray counterpart. This is purely X-ray. So without EP, we won't be able to detect these guys. But this one has a supernova association. So it is just like a gamma ray burst, but somehow this gamma ray burst jet is not energetic, not hard enough to be seen in gamma rays. It just produces softer and less energetic emission. And the supernova itself is quite standard, similar to other type 1c supernovae. And this one, it is soft. It is also low energy. So this is so-called Amati relation. So E iso versus E peak. So most GRBs are here. So this guy has almost the lowest isotropic energy and also lowest E peak. And this is another one. So they are all extension of this Amati relation all the way to the low energy, low E peak regime. Now, something surprising happened. Or not that surprising, but this guy also was not detected with gamma rays, which means E peak is pretty low. However, the redshift is high. It means E iso is actually not small. So it is not extension of Amati relation. It is something below. And we start to see quite a few of these. And if we really work on the light curve modeling, it is not off axis. So the jet is actually beaming towards us, but it's just very soft. So these are called dirty fireballs, which means it is still a successful jet, but it's dirtier. So GRBs have a Lorentz factor of greater than 100, and these guys have a Lorentz factor of, say, a few tens, like 30, for example. So these are all type 2 fast X-ray transients. And how about type 1, which means neutron star mergers fast X-ray transients? So this was the one I expected a long time ago. So this was my 2013 paper. I was saying that gravitational wave counterparts besides short GRBs and kilonova, we should have X-ray emission, simply because a lot of short GRBs have this X-ray plateau lasting for hundreds of seconds. Then what if we miss the jet, we only see the plateau? So then if that's the case, then gravitational waves should have a long duration X-ray counterpart associated with gravitational waves. So that was my APJ letter published in 2013 January. And later, Wei-Ming Yuan told me, who's the PI of the EP, he told me back then he was writing the proposal for Einstein probe. And he was trying to say, how can I make a connection with gravitational waves? And it turns out that my paper just came out. So it became one of the motivation of the, one of the three main objectives of the mission. But do we actually see these guys? Very excitingly, recently we detected one of them. This is still a short GRB, so it has a gamma ray burst, so very short. However, in the X-ray band, it is very, very long. So it is exactly what we expected. So this is a neutron star merger, make a brief short GRB, but there's a magnetar central engine, and this central engine lasted for 500 seconds. So 562 seconds. So this is the case that a type 1 EFXT with a short GRB association. And there are also two other cases without the short gamma ray burst, but duration is also long, and in terms of position, it is consistent with short GRBs. So this remains to be confirmed, and eventually we need gravitational wave data. So hopefully in 05, we see a neutron star merger and also a long duration EP event. So that will nail everything down. So these are type 1 and type 3. So very interestingly, these fast X-ray transients also happen in supermassive black holes. So for example, this event is the jetted TDE consistent with the white dwarf being disrupted by intermediate mass black hole. This nicely modeled by that model, and it was published in the Science Bulletin. And not only we have one TDE events, we also have a few mysterious ones. So if we just look at the X-ray trigger, it does not look like that different from other type 2 ones. It's also 100 seconds, same photon index. But if we start to look at the data, surprisingly, not only we have X-ray emission after that trigger, there was emission before that. So that already ruled out all the, say, catastrophic events, stellar mass type of the events, type 1, type 2. It has to be something which has been there for a long time, and then suddenly something comes out. So that underlying engine, my best guess is the supermassive black hole. So it's like AGN. And indeed, there was one case. It is a AGN, and then suddenly there is a 100-second duration X-ray burst. So these type 3 events are very mysterious, and we are writing a paper trying to interpret this. So, and how to make type 2, but majority of them are type 2. So this is also so we are writing a long paper to discuss all kinds of fast X-ray transients. And for type 2, these are 6 possibilities. The first one is a successful jet. We are looking down here, but it is just simply high redshift. If you shift the same gamma ray burst to a higher and higher redshift, it will become a fast X-ray transient. The second one is a successful, but it's the dirty jet. So this is the dirty fireball. We already detected one of these. And another one I call 2A, 2B. So this one is successful but weak jets. So these are the extension all the way to the lower corner of the Amati relation. And also, we can have a successful jet but viewed off axis. And we can also have unsuccessful jet. The jet never came out, but there's a relativistic shock breakout. And finally, we don't even have a jet. We just have a supernova explosion and that supernova shock breakout and make X-ray emission. So this one has been detected, this one. So we have a few already been detected, and all the others are still speculations. So this is what I can say. At least some fast X-ray transients are produced by successful weak jets. At least some are dirty fireballs. Shock breakout transient just discovered. So this was posted on arXiv. This led by PI Weiming Yuan, and Yu is actually also a co-author of this paper. And this is the dirty fireball paper, which should be published in Science, maybe hopefully later this year. So you can see that Einstein probe really opened a completely new window and start to see all these different types of objects. And we as theorists are trying to put pieces together and try to figure out the global view. Very quickly, story number 3, fast radio burst. I already mentioned this in the morning, so I will skip all the details, what, where, and how, and so on. But I want to say this multi-messenger part. So FRBs, as I said, they're magnetars. They are repeaters. They're not supposed to have gravitational waves. So in general, FRBs are not good emitters of multi-wavelengths or multi-messenger emitters. They're not good at doing that. But it does not mean that you cannot have those. Maybe a very small fraction of FRBs can be produced, say, through mergers. So this plot is saying that they're multi-wavelength counterparts, but the bottom line is they're not very bright during FRB, but before or after it might be bright. But this is more interesting. So all these mergers, neutron star mergers, neutron star black hole mergers, black hole mergers, so in principle, they can have something like FRB produced. So there are different ways. Before the merger, we have unipolar induction reconnection. We have charged CBCs. So during the merger, there might be something going on. Even, say, decades to centuries before the merger, the 2 neutron stars, the magnetospheres are already interacting with each other, there could be reconnection, there could be something going on to produce FRBs, because FRBs are cheap. They are not that energetic, so you can produce those. Or after the merger, you can make a supramassive neutron star and collapse into a black hole, and you eject the magnetosphere and make a FRB. Or you can make a stable magnetar and you can make FRB that way. So there could be a lot of possibilities to produce FRBs associated with mergers. However, because of the event rate, if any, only a very small fraction of FRBs can do this. But even if just one case discovered, we have profound implications. So this was the Blitzhard model. So this is after the merger, you make a supermassive neutron star. It's very heavy. It is rapidly spinning, but gradually slow down, and boom, it collapses into a black hole. But the black hole cannot carry magnetosphere. The magnetosphere is ejected, and then FRB could be produced that way. So in this case, there might be FRB following a GRB or following a neutron star merger. And then this was one case, GW190425, and the FRB, there was FRB discovered 2-point-some hours later. It could be a counterpart. And then there was another short GRB and the low far detected radio transient with this 76.6 minutes later. And yeah, so this is my favorite thing also, because Remo talked about charged black holes. So I can say that neutron stars can be charged because neutron star rapidly spinning magnet has a charge at the center. And once you have one of the component that is charged, when the two are gyrating and merging, then we naturally produce currents, and we can produce Poynting flux flow, dominated flow. And as the two getting closer and closer, the luminosity goes up. So this is the electromagnetic chirp compared to the magnetic chirp. So I call it charged CBC. And depends on this Q value, we can produce something of order of the FRB, even though it's much weaker. So I think that's all about it. I touched the three stories of the multi-messenger emitter. And finally, I would conclude that we are entering an exciting era of multi-wavelengths and multi-messenger astrophysics, and young scholars. It's an exciting time. So thank you very much.
Very, very exciting and rich. And everyone got a message. And in my case, I got an important message. We will start to look very attentively to this Einstein probe, because I think the data that you have shown tonight, they represent something extremely interesting. On the other side, making a general statement, I would like just to prepare for next year. All this is very beautiful. But there is something which is going on, which you have in the last few days, 2 days, yesterday and today. Riccardo Giacconi always told me that this point was that the universe is violent, a violent universe. This is the opinion of Riccardo. And you share that point of view, a violent universe. But there is something new since few weeks or few months which make us thinking that there is another part of the universe which is distinctively different because it's very gentle. And for many years, people have been looking at the galactic center, trying to find a black hole, violent, possibly meeting. But what is coming out is that at the center of our galaxy, we knew that there was something special because we saw a lot of maser, very, very delicate in the center of the galaxy. Delicate. And this message is coming out now with the dark matter component of the red dots. And with Wang Yu, we have been studying the possibility that exactly this dark matter black hole are so gentle that they guarantee in many spots in the universe island of tranquility, like in our galactic center, which could represent the seed for life. But all this is to be seen, is already a reality in the recent months' publication. And I hope very much that this message of a gentle universe eventually with dark matter and with red dots takes over momentum and maturity for the next Grossman meeting that we will lead together. Okay. Let's see if there are question and answer. Any question? Yes.
Neutrinos. So are you planning to build a...
Can you come here?
Yes, thank you. Very nice talk. So, were you planning to build some facility in China for neutrino detections? I heard something rumors about neutrino detectors, but are there any specific plans?
Yeah, I know at least two proposals. One from the South China Sea, the other is in the Pescara Lake, and they're all being planned. Yeah, in terms of sensitivity, should be comparable or maybe better than Gen 2, IceCube Gen 2. Yeah. But it is a long shot, so maybe another decade or so.
Okay, thank you.
Thank you. It was very impressive, your talk. I have a question. Do you, you touched in the beginning on one of your slides, strong QED effects. And what about observational evidences of these regimes in astrophysics?
QED, yeah, very...
There were Feynman diagrams in one of your slides. It was.
Yeah, it's
but,
just
here. It was
yeah,
some indication, discussion of vacuum polarization. What is the situation now?
Yeah, very, very good question. So, astrophysicists, we use some QED equations, for example, cross-section, Klein-Nishina in the strong magnetic fields. But recently, I should say, there's a progress from the X-ray polarimeter, which seems to be consistent with the vacuum polarization emerging from neutron star surface. I think that probably is a direct connection. And there's also another interesting subject is the photon splitting in a very strong B field. High energy gamma rays are not supposed to exist. They split so that they cannot produce electron positron pairs. So that's why the magnetars are not radio emitters. But that viewpoint is challenged recently because we start to see quiescent radio emission in some of the magnetars after the fast radio bursts.
And another question, in one of your slides, you touched the problem of not observed neutrinos. And equation which you wrote, it's the same equation which describes GZK limit, Grazin-Zatsepin-Kuzmin limit for highest energy cutoff of cosmic rays, ultra high energy. What is your opinion about this problem, and what is today's situation with GZK, and whether what you touched is related to this problem?
There's two separate problems. The non-detection of neutrinos from the gamma burst is mostly because the emission region is far away. The optical depth for P-gamma interaction is small. Because the neutrinos for typical GRB parameters, they have energy of PeV neutrino, which is still the cosmic rays that produce those PeV neutrinos are not ultra high energy cosmic rays. So I think that part we understand is because the composition of the jet is magnetic dominated, so emission region is very far away. As for whether GRBs are ultra high energy cosmic ray emitters, I think it's not affected. So according to the standard internal shock scenario, or some external shock scenario, GRBs are probably the best case that you can produce ultra high energy cosmic rays. But the non-detection of neutrinos does not hurt that judgment because we can, in principle, produce at different size. So even if the jet is Poynting flux dominated outflow, as long as you can accelerate particles based on the Hillock plot, there's no problem to that high energy, then should be still okay. So I think GRBs are still a viable candidate to produce ultra high energy cosmic rays.
And then some comment, not question. Recently, it was observed by team where Japanese are Amaterasu effect. It's above GZK cutoff limit, ultra high energy cosmic rays. They are observed according to the authors of this discovery because of the sources closer to our galaxies and from the cosmological distance. It is in your collection of multi-messengers universe.
Okay. Okay, thanks.
Let's see if there is anybody else. Yes?
Beautiful lecture. In this general picture that you outlined, is there any place for graviton-photon conversion and vice versa?
Graviton-photon conversion. Frankly, this is out of my scope. I haven't really thought about it.
Okay, let's see. Next question. If not, let's. Time is going. Oh yes. Very brief question. Dark matter. What's your opinion?
Dark matter from these things, these objects. Dark matter, they're distributed at much larger scales. So in the small scales like this, probably this is not very relevant. But yeah, so people talk about how to use GRBs to probe dark matter, but I don't see a very direct link.
We are dedicating a large part of this meeting to dark matter, therefore just follow the lecture. And we are making real progress in this house. Okay, if there is no extra question, And I thank the beautiful lecture speaker tonight, and let's be ready tomorrow. We will have news on gamma ray burst in the morning, and then all along we will continue with very interesting session. Thank you again, and let's look forward to next year in Hong Kong.
Yes, yes, yeah.
But we will come there before.
Yes, yes,
Okay.
anytime, anytime. Yeah, thank you.
Okay.